All right, you crazy kids, here's your lecture on oxidizing and reducing agents and half reactions. Half reactions, you have two technically half reactions that make up a redox reaction. You have the half oxidation reaction and you have the half reduction reaction. I'm going to teach you guys how to take your whole reaction and pull out the half reactions that make up that full redox reaction. Let's start by making this a little bit more real. Last time last video, we were just assigning oxidation numbers and then figuring out what's oxidized and what's reduced. To do that more accurately, we need to look at a net ionic equation. So here's my reaction. You guys should have the ability to do that net ionic equation. You can pause and try it on your own. And here's your precursor to the net ionic equation. What we were doing a long time ago when we did net ionic equations is simply crossing out things that appear on both sides of my reaction. We said that they were spectators, they didn't really change. Well, they didn't really change because their oxidation numbers didn't change. Let's take a look at what that really looks like. So if I did my oxidation numbers, zinc's a 0 and gold's a 0, individual elements. Ions, individual ions, the oxidation number matches the charge. So that's +3 there and that's +2 there. Let's take a look at this nitrate. We have 3 oxygens. Each oxygen is -2. That's a total of -6. Your oxidation number has to equal your charge. So that means nitrogen has to be +5, while oxygen is -2. And we have the same thing occurring here. This is still +5. This is still -2. Because their oxidation numbers did not change, they are truly spectators. Nothing really occurs there, and they're not involved in our net ionic equation. So at first glance, it looks like zinc goes from 0 to +2. How would it do that? It would have to lose electrons. That means zinc's being oxidized. And really, I care about the half reaction, and the half reaction is going to include how many electrons it's actually losing. So to go from a 0 to a +2, you would have to lose 2 electrons. And we're going to show the loss of 2 electrons as a product. If you're losing those electrons, it's a product. Gold, on the other hand, it's going from a +3 to a 0. That's a reduction in its oxidation number. That means it's going to be gaining electron. How many electrons? I would have to gain 3. When you gain electrons, it is a reactant. You're gaining those electrons. That is how you pull out your half oxidation and your half reduction reactions. You show the total number of electrons that are lost and gained, you show the change of it, and you write this little calculation that I've shown you there. So this would be a great answer for a reduction half reaction. And this is a great answer for your oxidation half reaction. Hopefully you guys can see how I got that information. For the reducing agent and your oxidizing agent, it's the thing that causes the action. So what I mean by that is it's switched. Whatever's being oxidized is defined as the reducing agent. The reducing agent causes oxidation. That's how it's defined. If we look at it, zinc is being oxidized. Here it is. That means zinc in my original, let's use a different color here, and my original equation is, by definition, the reducing agent. Okay? This gold here with the 3+ charge is being reduced. That means it's causing the oxidation, so we define that as the oxidizing agent. But not just gold, it's the whole thing. It's the thing you start with. So here's my oxidizing agent, and here is my reducing agent. Remember, it's switched. Whatever's being oxidized is the reducing agent, and whatever is being reduced is the oxidizing agent. That's how that works. Let's take a look at another example. Oh, I don't think I mentioned it, but these are all not balanced. So just be aware that I'm doing unbalanced half reactions. When you start to balance them, it gets a little bit more tricky. We're going to leave that out, mostly because it's easier in person to explain. And it's not really a requirement for your first year chem. Here's our second example. So we have this big, long, scary reaction. Remember, we need to look at a net ionic equation to kind of make this make sense. So you guys could pause and try to do a net ionic equation on your own. Here we go. I bet you a bunch of you try to split apart things that don't split apart. This is a weak acid, that would not split. This is a covalent compound, that would not split. This is a covalent compound again, that would not split. Remember, you're only splitting things that are ionic compounds in solution or strong acids and strong bases. So H2S is a weak acid, it would not split. All right, let's go ahead and assign all of our oxidation numbers. So H2S, what are we going to do there? Sulfur is a -2 charge. Hydrogen is going to be a +1 charge. Here we have a hydrogen ion. A hydrogen ion matches its charge. We have NO3, nitrate again. From last time we explained that to be +5 and -2. Oh, 2 hydrogen charges. Okay, still +1 oxidation number. All right, now SO42 negative. Each individual oxygen is 2 negative. There's 4 of them. That's a total of 8 negative. I need my overall charge, my overall difference in my oxidation number to match the charge here as -2. So that means sulfur has to be a +6. Oh boy, let's try to zoom in on that, clean this up a little bit. -2. +6, -2. Awesome. NO2. Each individual oxygen is going to be -2. There's 2 of them. That's total -4. So nitrogen has to be +4. And H2O, oxygen -2 once again. That means each individual hydrogen would be +1. All right. Whoa, big kind of mess here. Let's see if we have any spectator ions or instances that the oxidation numbers don't change. We will cross them out in hot pink. Hydrogen is +1 on both sides of my equation, here and here. And believe it or not, I can cancel out water here. I can do that because its hydrogen is +1, same charge here, and also oxygen is -2. Oxygen is -2. Because the charge, or not the charge, but the oxidation number on both components of that compound do not change, it's still considered technically like a spectator or something you would not involve in your half oxidation, half reduction reactions. Now, we have to dive into what's being oxidized and what's being reduced. We'll do green for this thing here. So for this thing here, my sulfur is going from -2 to +6. How would sulfur go from -2 to +6? It would have to lose a bunch of electrons. Oxidation is loss. There it is. How many electrons? -2 to +6. That's a total of 8 electrons lost. So there's your half oxidation reaction. I start with my 2 components and I add in the difference in my electrons. Remember, if that's the oxidation, that means that thing, whatever caused the action, is your reducing agent. And there it is, H2S. It's whatever you started with in the reaction. So here, we'll do red. Right? Here's the thing I started with. That is being oxidized. That means that identity is the reducing agent. Here it is in my original equation. Now, what's the other half reaction for redox? Nitrogen goes from +5 to +4. Oh, okay. That's a reduction in its oxidation number. Because it's a reduction in its oxidation number, a difference of 1 electron, it is being reduced. And there's the location of that electron. What's being the oxidized agent, or how can we identify the oxidizing agent? All right, this thing right here started as this. So hopefully that is my oxidizing agent. Let's take a look. Good news it is. Looks like I know what I'm talking about. These are not balanced once again. All right, here's the last one. You guys should be able to do this all on your own. So here's this big, long, scary looking thing. You're going to be doing a nanionic equation. You should pause right now and try that on your own. All right, here's my nanionic equation. I removed everything that doesn't change in terms of an oxidation number. And now I can pull up my half oxidation and my half reduction. There they are. And then once again, we will have what's the reducing agent and oxidizing agent. And there they are as well. Take note that iron is being oxidized. That means this component here is the reducing agent. And looks like manganese is being reduced. There's the original component. So that's your oxidizing agent. Hopefully you guys enjoyed these videos. It makes a little bit of sense. You'll have some homework on these. See you on the other side.